I'm going to introduce to you Big O and her sisters. Those are used when it comes to analysis of algorithms. For some students, Big O is really a big headache. They find it difficult to understand. So I will try to make it as simple and as easy as possible, so that at the end of the lecture you will like using Big O and her sisters, and you'll be comfortable using them as well when it comes to analysis of algorithms. The Big O is used for either estimate the number of operations an algorithm uses as its input size grows, or to compare the efficiency of two algorithms. And we are going to only consider functions with non-negative domain and range. The reason being is that the input size and the number of operations for any algorithms are positive numbers. First, I'm going to start with this simple example. I am comparing 10n squared with 2 to the power n. So I have two algorithms. They solve the same problem. One cost 10n squared operations. The other cost 2 to the power n operations. So make a table. N is 10. N is 1, that's 10, that's 2. The cost here is higher than here. 2, 44, 3, 98, 10 times more. Keep going, 5, 250, 32, much larger. Then when you come to 10, something changes now. 1000 is less than 1024. This becomes more costly than this. 11, the same thing, almost twice. If I continue at n20, 10n squared is 4000, while 2 to the power n is 1,048,576. So you see, what is really of interest to us is not for small values of n how an algorithm behaves, is what happens when n gets larger and larger. Then we can see the difference. Now, in this case, this algorithm here that solves the problem with 10n squared is cheaper, is much better than this algorithm that solves the same problem with 2 to the power n operations. Okay, now we come to the definition of Big O. Big O, then we say that F is slower than G, grows slower than G. F and G are from N or R positive to R non-negative numbers to the non-negative real numbers. So Fx is Big O Gx if you can find two constants, C and K, positive, such that Fx is less or equal than C Gx. So Fx is bound from above by Gx. And now it's very easy to see that the C and K are not unique. Here's an example. I am comparing this function, 3n cubed minus 2n squared, with this function, 10n plus 11. So when you look at the graphs, this function here is smaller than this function here up to this point. From this point up, this function becomes smaller than this function. See, Fn is less or equal than 1 Gn. For any n greater or equal than 3. So from 3 and up, this function is less or equal than this function. I'm going to be giving you several examples so that you understand the concept. Here's the first example is 1 plus 2 plus 3 up to n is big O n squared. Simple. We put this here and we say this is less or equal than, each term here is less or equal than n. So n plus n plus n times gives you n squared. In this case, you can see c is 1 and k is 1. Another example, 7x squared plus 2x plus 9 is big O x squared. We do the same thing. We try to find an upper bound. 7x squared, 7x squared. 2x is less or equal than 2x squared, provided that x greater or equal than 1. And the 1 here, 9 times 1, this 1 is less or equal than x squared. So you add 7 plus 2 plus 9, you get 18. So c is 18 and k is 1. Now, it's very important. If x is 1/2, x squared is 1/4. It's smaller. For x squared to be larger than x, x must be greater or equal than 1. Here's another example. 7n squared plus 10,000n is big O n squared. Why? We do that. I know that n is less or equal than n squared. Add 7 and 10,000. 10,000 and 7, n squared. So c is 10,007 and k is 1. Now this example, we're going to solve it in a different way now. The same example. So I'm going to put that here, but I'm going to say that this 10,000 n is less or equal than n squared, provided that n, if this 10,000 here less or equal than n, then when you times it, it will be less or equal than n squared. So you get 7 plus 1, 8n squared for any n greater or equal than 10,000. You see, now the c and k are different than the previous example. That's okay. That's okay. You can get different answers for the same problem. Here's another example, a fraction. I want to find a big O estimate for this fraction. I put it here. Then I need to get something larger than here, than this up here. So I replace 3n by 3n cubed. And I need to have something smaller than this. I put 7n. So this one is less or equal than this. You add these two terms, you get 11n cubed divided by 7n, simplification, and you get c to be equals to 11 over 7, and k is 1. Therefore, this fraction is big O n squared. Pretty simple. Now, 8x squared is big O x cubed. And it's going to be big O x to the power 4, x to the power 5, because x squared is less or equal than x cubed, less equal than x to the power 4, provided x greater or equal than 1. So you can set it up this way. You find c is 8 and k is 1. Now here's a problem that some students have some difficulty with it. N squared plus 10n is not big O n. Okay, how do you prove that? We use a technique known as proof by contradiction. And I have a whole video about this topic. You can go and take a look at it. So I'm going to assume that n squared plus 10n is big O n. Then what happens? Then I can find a c and a k. This means they exist, okay? A c and a k in R. C is positive, k is positive, such that n squared plus 10n less or equal than c times n for any n greater or equal than k. So now I'm going to simplify by n, here and here and here, so I get n plus 10 less or equal than c for any n greater or equal than k. Is that possible? It's impossible. It's impossible to say that for any n greater or equal than k, n plus 10 will still be less or equal than c. It's impossible. Why we got this problem? Is this impossible? Because we assumed that n squared plus 10n is big O n. Therefore, n squared plus 2n is not big O n. Here's another example, very simple. We're using the same kind of technique. Factorial n is big O n to the power n. What is n factorial? 1 times 2 times 3 times n. Each one of these terms is less or equal than n. I put it here. N times n is n to the power n. It's n times n times n. N times, that gives you n to the power n. So c is 1 and k is 1. Here's another example. Log factorial n is big O n log n. Why? In the previous example, we found out that factorial n is less or equal than n to the power n. Then you take the log of the two sides. Log n to the power n is n log n, and therefore log factorial n is less or equal than n log n. So c is 1 and k is 1. Now, this is very important that log n is lower than n. It grows slower than n. Log n is less or equal than n. And here the log is base 2. So we know this, we can show this really easily. N is less or equal than 2 to the power n for any n. So therefore you take log of both sides. Log n is less or equal than log 2 to the power n, which is n log 2. N log 2, log 2 is 1, so it's equal to n. Therefore, log n is less or equal than 1 times n for any n greater or equal than 1. So your c is 1 and your k is 1. Okay? We keep going. Properties of big O. Let me make sure I did not skip any. Yeah. Properties of big O. Here are some interesting properties of big O. Transitivity of big O. If f is big O G and G is big O H, then f will be big O H. This is very similar to if x less or equal than y and y less or equal than z, then x less or equal than z. Okay, transitivity of big O. Here are the addition and the multiplication. Preserve big O. So f1 big O G1, f2 big O G2, then f1 plus f2 is big O G1 plus G2, addition. And f1 times f2 is big O G1 times G2. Now, if it happens that this G1 and G2 are the same, then f1 plus f2 will be big O Gx, and f1 times f2 is big O G to the power 2x, addition, multiplication. And sometimes we use the addition in this way here. f1 is big O G1, f2 is big O G2, then f1 plus f2 is big O, the maximum of G1x and G2x. And we will see how these are applied in these few examples that I'm going to be giving you. Now, all of these can be really proven very easily using the definition. Nothing really difficult about them. Okay, now we are going to do some examples here. give big O estimates for this function here. See, this piece here is big O n squared. Log n, you times these two, Log factorial n, we just found it earlier that it's big O n log n. 5n is big O n. Now you see, you multiply these two here, n times n and n squared. Now I have two functions. This one is big O n squared. Big O n squared, when you add them, is big O the same g, n squared log n. And if you want to do big O n cubed, that's fine because log n is big O n. Now log n, this is a very interesting, an important theorem or lemma, if you want to call it. Log n is big O n to the power epsilon for any epsilon positive. And the proof of this is kind of a little bit difficult. It requires calculus to prove. So we just use it and we accept it as correct. So log n is big O n to the power epsilon for any epsilon. So if epsilon here is 1/2, 1/4, 0.0001, log n will still be less or equal than, will be a big O of that number, okay? Now, I'm going to prove this theorem for you because some students have problems understanding it. Log to the power k grows slower than n to the power epsilon for any epsilon in R positive, for any k in n. So, which means log to the power, this is a power, log to the power k n is big O n to the power epsilon. How do you do that? When k is 0, it's simple. Log to the power 0 is 1, and 1 is less or equal than n to the power epsilon. When k is positive, here's the trick. I'm going to write log n is big O n to the power epsilon over k. That's using the lemma I just mentioned earlier. Why I'm doing this? Because I'm going to multiply log n by itself k times. Log to the power kn, log n times log n times log n, that's k times. So I put this, the same here, so when you multiply this k times, it gives you n to the power epsilon, big O n to the power epsilon. So very important to remember this theorem. Here's an example here, give big O estimate for this function. I can look at it really simple. This piece here is n4, nothing about it. This piece here, two functions. This one is big O n, and this one, even though to the power 10, it's still big O n. See? O n, that O n squared, O n4. The maximum now, we are using the maximum of n4 and n2, big O n4. Very straightforward. Okay, this is another example. Let's prove that log x cubed plus 1 is big O log x. Okay, you put this one here, less or equal than x cubed plus x cubed, because 1 is less or equal than x cubed, x greater or equal than 1, remember that. 2x cubed, you take the log of both sides, you get log 2 plus log x cubed, log 2 plus 3 log x, and if x is greater or equal than 2, then you can have log 2 will be less or equal than log x. So you will have log x plus 3 log x, 4 log x, and it's done. Your c is 4 and your k is 2. Okay, here's another example, very straightforward again. Look, this is x5 is going to stay x5. X to the power 3 is going to stay x to the power 3 until the end. Here's the problem. I have the product of two functions. This one here will be x. This one here, I just showed it to be log x, big O log x. Times these two, big O log x is big O x. Log x is big O x. So transitivity, okay? And then you have OX, and OX here, that's OX squared, and then you have OX cubed. You are adding now, the maximum is x cubed, Here are some of the most commonly used functions in when it comes to big O's. So from most efficient to least efficient: O1, O log n, On log n, On squared, O to the power n, and O factorial n. And these are the functions. How you see this one is smaller than this, smaller than this, smaller than this, and so on and so forth. Now, the ratio of each function and a succeeding one tends to 0 as n goes to infinity. Now, this is an interesting example. We're going to assume that the machine does 10 to the power 11 operations per second. 10 to the power 11 operations per second. Now, I have log n, n log n, n squared, 2 to the power n, and factorial n. So when n is 10, fraction of a second, fraction, all of these are really good. All of these are fraction of a second. When n is 100, here's what happens. Fraction of a second. Here, 2 to the power n is 10 to the power 11 years. It's not a joke, years. And remember what I was doing earlier at the very beginning. I was comparing n squared with 2 to the power n. Even though I multiplied by 10, it doesn't really matter. So 2 to the power n is not a joke. It grows really, really quickly to very, very large numbers. Now, I sometimes ask my students, if I take a paper like this and cut it in half, put them together, cut it in half again, put them together, cut it in half, and put them together. If I do that 50 times, and I ask him, how much you think the stack would be, how thick would be the stack? Some student would say 2 feet, 3 feet, 1 feet, 10 feet. If you do the math, you will find that the stack will be, more than the distance between the Earth and the Moon. So 2 to the power n is really a problem. So, and factorial n, don't even think about it. So if you continue here up to 10 to the power 6, what's 1 million? So you're solving a problem of size 1 million. So log n will do it in fraction of a second. N fraction of a second. N log n, this is called polynomial growth, okay? It's still fraction of a minute. It's not too bad, but nothing here. You can't really count on one of these here. You can't use those. Now, here's an example where I have a machine that does 10 to the power 9 operations per second. And what is the largest n for which the algorithm can solve the problem within 1 second? For these cases, I have 5 functions: this, or this. All what you have to do is take log n times 10 to the power negative 9. You put this to be equal to 1. This is your equation that you need to solve. Okay? And which means log n is 10 to the power 9. You find n to be 2 to the power 10 to the power 9. That's a huge number, so that solves a really big, large number, large problem. Here's the second one. You get n to be 10 to the power 9. In log n, you get n equals 3.96 times 10 to the power 7. N squared, you get started to be smaller than 31,623. 2 to the power n, only 29. Factorial n, only 12. Okay, now I'm going to introduce one of the big O's sisters, is big omega. The same situation here, and we say fx is big omega gx. If again there is a c and a k positive from R, c is positive and k is positive. this means they exist, and this means belongs to, okay? So now fx is greater or equal than cgx. Fx is greater or equal than cgx for any x greater or equal than k. So now I have a bound below to fx. Again, c and k are not unique, and you will understand now if x less or equal than y, then y greater or equal than x. That's exactly what we're doing. So now, here's what you need to keep in mind, that fx is big omega gx is equivalent to gx is big O fx. Okay? Fx is big omega of gx if and only if gx is big O of fx. They're very, very related, okay? Here's an example. Show that this one is big omega. Now, if I look at this term of big omega x to the power 3, if I look at this term here is positive when x is greater or equal than 2. When you put x2, you get here 12 plus 4, 16 minus 13, positive, which means this will be greater or equal than 5x cubed. So your c is 5 and your k is 2. What are the properties of big omega? The same as the properties of big O. Transitivity, addition, multiplication, the same properties. Now I'm going to introduce another sister to big O is Big-Theta. Big-Theta, and that is really a good sister. If we can use it, if it applies, it's really good because it shows that the two functions are of the same order. They grow at the same rate, and that's important. So again, f and g are from n or from r, non-negative real numbers to non-negative real numbers. We say that fx is big theta gx. If you can find a constant, two constant, 3, c1, c2k, c1 positive, c2 positive, k positive, such that, look at this here now. I put fx like in a sandwich between gx here and gx here. You see, now when you look at this piece here, this means fx is big O gx. When you look at this piece here, this means fx is big omega gx. So at the same time, fx is big O gx and big omega gx. Then it becomes big theta gx. And that's explained here. F is big theta gx if and only if f is big O and f is big omega at the same time. And obviously very simple to see. F is big theta g is the same as g is big theta f. That's why we say they grow at the same rate. They are of the same order. So now you have an algorithm and you find out that the number of operations is 1 plus 2 up to n. Earlier I proved that is big O n. So now I'm going to prove that this is big theta n, I showed it to be big O n squared. Now I'm going to show it big theta n squared, which means my function, this function here, is at the same rate, same speed as n squared. And n squared is a really nice function. So what I do here is really simple. I'm going to put fn, this summation here, summation here, 1 plus 2 up to n. I'm going to reorder it going downward from n minus 1 to 1, and then I'm going to add. I'm going to add these two, I get n plus 1. 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 How many terms? N terms. So which means 2f twice, because I added these, 2fn is n plus 1, n times n plus 1. Therefore, 1 plus 2 plus 3 plus n is n times n plus 1 divided by 2, n plus 1 over 2. So if you want to add 1 plus 2 plus 3 up to 100, the answer would be 100 times 101 divided by 2. 50 times 101. So now I take this function and put it in the middle here. That's the same function, same function. So I'm going to look at something a bit larger than this. So n over 2 is smaller than n squared over 2. N squared over 2 plus n squared over 2, that gives you n squared. To the other side, since this one is positive, this will be greater or equal than n squared, half n squared. So now you see how I put fn between half n squared and 1 n squared. Therefore, I solved the problem. F is big theta n squared. This is k is 1, and that's C1, that's C2. Okay, let's prove that this one here is big theta n squared. Well, this is here plus 5 log n. This will be less or equal than 8 n squared. Why? Because log n is less or equal log n. So 5n squared plus 3n squared, 8n squared. On this side now, since this one is positive, then this would be greater or equal than 3n squared. So you C1 is 3, C2 is 8, and K is 1. Properties, no, still, let's do this here. I'm saying that this function here is big theta n to the power 5. Why? Because if I put the function here, I know this one is greater or equal than 8 n to the power 5, because all of this is positive number. This one is positive, okay? So now, and that's less or equal than 49, which is 7 plus 5 plus 2 plus 11 plus 13, 49 n to the power 5. So that's your C2, and that's your C1, and your K is 1. Your K is 1. Order of polynomials. This is very, very important. Any polynomial of degree n, that's why I put here a n different than 0, is big O x to the power n. Is big theta x to the power n. Okay? Big theta x to the power n. See how now we can immediately solve this problem. This polynomial, I look at the highest power 7, so that would be big theta n to the power 7. This one here, big theta n to the power 99. This one here, big theta n to the power 11. Okay, properties of the big theta, the same as the big O and the big W, big omega, in terms of the addition and the multiplication. But what is now new, and it only applies to big theta, is the division. Provided that f2x is different than 0 and g2x is different than 0 for all x, then if f1 is big theta g1 and f2 is big theta g2, when you divide, you get big theta g1 over g2. And that's a division. Let's see how this can be applied. Look at this. Very simple. Above here, we just earlier showed something similar to that. This big O n to the power 5. A big theta n to the power 5. Down, big theta n cubed, polynomial. So n5 divided by n to the power 3, you get n squared. Here's another example. Same thing. Up is big theta n cubed. Down is n cubed. N cubed divided by n cubed, that n to the power 0, that's 1. Big theta 1. Another example, the same thing up here is big theta n to the power 5. Down is big theta n to the power 7. When you divide this by this, you get n to the power negative 1, or 1 over n squared. Okay? Now the last two sisters I'm introducing is the little o and the little omega. And little o means f grows strictly slower than g. And little omega, f grows strictly faster than g. So exactly the definition is really simple, because once you know this, it's okay. So fx is little o gx, two things. Fx is o, big O gx, and fx is not big omega gx. Here, sorry, come on, I have to wait until it goes away, I guess. Here, fx is little omega gx means two things. Fx is big omega gx, and fx is not big O gx. Last example, I have this function from n plus to n plus. Is fn big O n, big omega n, big theta n, little o n, little omega n? Okay, I take this function here, put it between, I said this is less or equal than n plus n. Obviously, this one is less or equal than n, okay? And greater or equal than n, because this one is positive. So what I did, I put fn between n and 2n. For any n greater or equal than 1. What that tells me, that fn is big theta n. So when it's big theta n, then it's going to be big O n, and it's going to be big omega n, no problem. But then it's not going to be little o n, it's not going to be little omega n. Now, for those of you who likes calculus, here are the definition using calculus, okay? Equivalent definitions. You take the limit as n goes to infinity, fn over gn, L. You have three cases. Remember, we're dealing with positive functions, okay? Otherwise, you have to take the absolute value. So, L could be 0, greater than 0 but finite. L could be infinity. If L is 0, then here's what happens. Fn is little o gn, which means also big O gn. If L is greater than 0 but finite, Fn is big theta gn. And if L is infinity, then Fn is little omega gn, which is big omega gn. If I take the example I did before, I take the limit between n plus 1 over n divided by n. The limit here, this will be 0, you get 1. So when I'm in this situation here, therefore Fn is big theta n, and that's what we showed earlier. And that's the end of Big O and her sisters. In a future video, I will be talking about analysis of algorithms, how to apply the Big O and her sisters to algorithms, and how to use them. So I hope you enjoyed the lecture, and thank you very much.